Hello and welcome back to another AP Precalculus review video. And today I'm be going over this AP Precalculus exam review, which I created. I will have this linked in the description. But the AP exam for 2026 is tomorrow. So it's kind of last minute, but I will have this posted in the description if you want to look over it, just some last minute practice or review. This is the table of contents. So first I'm going to go over Unit 1, Unit 2, and Unit 3. Or first I'm going to go over Unit 1, and then we'll move on to Unit 2, and then on to Unit 3. So yeah. Alright, Unit 1 is polynomial and rational functions. So functions take in inputs and assign them to outputs. Domain is the set of all inputs, range is the set of all outputs. And the important thing to know, each input gets mapped to exactly one output. So you can't have one input mapping to multiple outputs. There are different ways to represent functions. I'm not going to go over them all, but it's good to know them. You don't have to know the definitions, but it's good to know how to use them. Rates of change is how it quantifies how much the output of a function changes, pretty much. So it's your slope of your m value. And your average rate of change gives the rate of change over an interval. If it were to change constantly over the interval. So, formula for that is y2 minus y1 over x2 minus x1. And for quadratic functions, the differences in function values over same-sided intervals change at a linear rate. So the rate of change over quadratic functions is linear. It's important to know. So here's some terminology. If it's increasing, the graph goes up from left to right. If it's decreasing, it goes down from left to right. Concave up, it's kind of like a bowl shape, and concave down, it's a frown shape. So concave up just means that the rate of change is increasing, and concave down just means the rate of change is decreasing. Okay. So local maximum is a place where locally a function reaches its highest point, and local minimum is the same thing but for a lowest point. And the global maximums is like the local, but it's over the entire function. Inflection points is where the function changes concavity, so concave up, concave down, vice versa. Alright, so x-intercepts occurs at the zeros of the function, so it's at something comma 0. And there are different ways to find that. Y-intercept is where across the y-axis. Alright, so there are different types of transformations. It's good to know these. Horizontal, it's always on the inside, and vertical is on the outside. I'm not going to go over everything in depth, because there's not time. But, yeah. And yeah. Always go from the inside to the outside. So you would start from x minus h, and then you move over to the b, and then the a, and then the k. That's when you're graphing it, when you're applying the transformations. So that's kind of the order, is from inside to outside. So different types of symmetries. Even symmetry means it's symmetric about the y-axis, so it's the same on both sides of the y-axis, and that happens if f of negative x is equal to f of x. And odd symmetry means symmetric about the origin, so f of negative x is negative f of x. So a standard form polynomial is this. It's a sum of a bunch of terms with decreasing powers. So the leading term is the term with the highest exponent. Degree is the highest exponent itself, and the leading coefficient is the coefficient in front of the leading term. The factored form shows all of the zeros of the polynomial. It tells you the multiplicity of the polynomial zeros. And multiplicity is just the number of times that a certain zero appears. That makes sense. Yeah, there's different types of polynomials. There are many different ways to find zeros. I'm not going to go through all of them. Yeah, I probably should have had this up here. Nah, it'll be fine. Yeah, multiplicity of 0 is basically just the number of times that it appears in a factored form. And yeah, this is what it looks like for multiplicity. So if it's single, it's multiplicity of 1, it goes through. Multiplicity of 2, it just touches. And then multiplicity of 3, it kind of snakes through. So it still passes, but it doesn't pass like it just crosses. It kind of snakes through and then passes. So second differences is the over in equal size intervals of inputs. It's the differences between the first differences. So for constant functions, it's going to be all be 0, obviously. For linear function, the second differences are always 0. But for quadratic functions, the second differences are constant but non-zero. So this can tell you what kind of function a given data is, based on just the second differences of the data. Okay, so yeah, here I think this is best at showing this. The end behavior of polynomials is determined by the degree and leading coefficient. So that's good to know. Alright, a rational function is a ratio of two polynomials. A whole is where it's not a vertical asymptote. It looks like there would be a point there, but there's not. It's kind of just, the function is not defined there, but it still gets really close to it. That's the best way I could explain it. A vertical asymptote is it kind of approaches infinity from the top and bottom, or from left and right. And this occurs at zeros of the denominator. And the zeros of the function occur at zeros of the numerator. So for the end behavior, if it all depends on the degree of the polynomial in the numerator compared to the polynomial in the denominator. So if the numerator is greater than the denominator in terms of degree, the end behavior is determined by the ratio of the leading terms. If the degrees are equal, that's a horizontal asymptote, which is just the coefficient in the numerator divided by the coefficient in the denominator. And if the degree of the denominator is greater than the degree of the numerator, then it just goes to 0 on both sides. And yeah, make sure you use limit notation. So limit, as this goes to negative infinity of f of x, that's just saying as it gets really, really close to negative infinity. So what a slant asymptote looks like, notice the degree of numerator is greater than the degree of denominator. Here the degrees are equal, so it's a horizontal asymptote. And here the degree of the denominator is greater, so it goes to 0. Yeah, make sure to know polynomial along the division. And yeah, if you have a polynomial, you can use polynomial along division to factor it. And also, when you're doing polynomial along division for a rational function, you can use it to convert it to another form that will it tells you what the, sorry, let me show you this. The quotient division is the end behavior, and the remainder is just, it goes to 0 at the ends. So basically the end behavior is just going to be whatever the quotient is, ignoring the remainder, for a rational function. Alright, binomial theorem, use Pascal's triangle. Here's the step-by-step instructions. So it would be good to go through and read this. I don't really have time to go through everything. But it's not a super important part. If it comes down to it, you could like expand it out fully, but this is a lot faster. So you just use the different rows of Pascal's triangle. So if you're trying to do something to the fourth power, you use the fifth row. And your coefficients would be 1, 4, 6, 4, 1. So you would have like 1a to the fourth plus 4 a cubed b, right? And you just keep, counting down the a and counting up the b and changing the coefficient. Anyways, on to Unit 2, exponential and logarithmic functions. A sequence is an ordered collection of numbers, which often follows a repeating pattern. So the initial term is the first term listed in the sequence, and there's two main types of sequences. Arithmetic, which means that the consecutive terms have a common difference, and geometric means that they have a common ratio / factor. So these are the formulas to find the nth term. So this is if you have a0, the initial term. This is just if you have ak. So this is if you have g0, and this is if you have gk. Basically, they're very similar formulas, but one is for arithmetic, one's for geometric. And it's just based on whether it's a common ratio or a common difference. Alright, yeah, so arithmetic sequences are very similar to linear functions, and geometric sequences are very similar to exponential functions. Yeah, so exponential functions change by constant factor, while linear functions change by constant rate. So that's the important difference. So characteristics of basic exponential functions: domain is all real numbers. The range, it depends on what the value of a is, but it's either going to be from 0 to infinity or negative infinity to 0. There's no x-intercept. It doesn't cross the x-axis, and the y-intercept is just 0, comma a. So whatever that initial value is. Yeah, a is the initial value, b is the growth factor. I should mention that. So this is what exponential growth looks like. This is what exponential decay looks like. Okay. End behavior is also determined by n b values. You should sketch the graph. And one end always goes to infinity or negative infinity, and the other end goes to 0. So e is about 2.718. It's important to know e, be able to work with that. It's just a type of constant. Alright, here there's some properties of exponents. These are good to know. Product property, power property, fractional exponent property, negative exponent property. You might need to use those to manipulate exponential expressions. So exponential models are good for modeling growth and decay. You can use regressions for that, or you can identify the initial value and growth rate. Compositions of functions, you use f on this little open circle g of x. So that just means f of g of x. So g of x is on the inside, so it becomes the input for f of x. So you evaluate g of x, and then you do f of whatever that is. F of g of x is not g of f of x. There are different things. And then f of x equals x is the identity function. Composing any function with the identity function yields itself. Alright, inverses. This is important. So an inverse of a function is a reverse mapping of that function. So the inputs and outputs are swapped. And a function only has an inverse if it is invertible. So every single output is generated by exactly one input. And you can use the horizontal line test to test that and see, because if the horizontal line passes through more than one point, sorry, this should be more than one point of the function is not invertible. Okay. So yeah, a function only has an inverse if it's invertible, and the domain can be restricted. Like for example, for x squared, you can restrict its domain from 0 to infinity on the invertible portion, and the inverse would be square root of x. So yeah, if a function isn't invertible, you can restrict its domain to get an invertible portion. Yeah, there's multiple ways to find the inverse of a function. I'm not going to go through all of them, but often you have to analytically do that. So you'll have to start with the equation and be able to work your way there. So swap the x and y values and then solve for y and then replace y with f inverse. Okay, so basically logarithms are the inverse of exponents. So if a equals log base b of c, then b to a equals c. If the logarithm base is not specified, it's 10. And then on a logarithmic scale, each unit represents a multiplicative change. So the general form for basic logarithmic functions is a equals log base b of x. B has to be greater than 0, b is not 1, a is not 0. Important, they can only take positive values, so negative values are not in their domain. It's important to know this behavior, so as the inputs for exponential functions change additively, outputs change multiplicatively, but is the opposite for logarithmic functions. So if you, like for example, multiply the input of a logarithmic function by 10, then the output will always, every single time, decrease or increase by the same amount. Alright, so this is what logarithmic graphs look like. No y-intercept, but they do have an x-intercept. Yeah, you can transform logarithmic functions. And this also can change the vertical asymptote that they have at x equals 0. So if you're translating it horizontally, that will like move the the vertical asymptote. Sorry. So there's some logarithm rules you should know. Log base b of x times y is what happened? Apologize. There we go. There we go. So log base b of xy, so x times y, is log base b of x plus log base b of y. So when you're multiplying on the inside, you're adding on the outside. And then when you have something raised to another power, so x to the y, and you take the logarithm, you can pull this thing in the exponent down outside. So y log base b of x. Log base b of x is equal to, oh yeah, this is for changing the base. So log base b of x, if you want to change it to some other base, log base a, right? Log base b of x is the same thing as log base a of x, so the new base, divided by log base a of the old base. There's a lot of stuff about logarithmic equations and inequalities. You should already know how to do this. I really can't go through all this. It's supposed to be a quick review. Generally, try and always solve with graphing for exponential and logarithmic equations. There's a lot of different problems you will find, but often if you have an exponential, you need to undo something. You need to use algebra, but you often also need to undo something with a logarithm. And for logarithmic equations, you need to undo something with an exponent. So like having both sides exponentiated with a base of whatever. And then for inequalities, it's like you do the process of solving it, and then you test in between all the solutions to see where it holds. Logarithmic function models are often showing up they often show up in places where the increase or decrease is slowing. And of course, pay attention to the context when you're creating a model. Semi-log plot, one of the axes is logarithmic scaled. Alright, unit 3, trigonometric and polar functions. Alright, periodic, it just means that it repeats, basically. Period is the distance of inputs that is needed for the function to repeat again. So if it's a periodic function f, so smallest value k, so it's a f of x plus k is equal to f of x for all x in the domain. Alright, and all the behavior and values of a periodic function are told in a single period of that function. So here are some examples of periodic functions. You can see sine wave, which is what we're going to be talking about. Alright, standard position just means one of the rays is on the x-axis and the vertex at the origin. And the other ray, or side, is the terminal ray. So positive counterclockwise and negative clockwise. Radian measure of an angle in standard position is a ratio of the length of the arc to the radius of that same circle. It's not super important. You probably don't need to calculate that, but anyways. Definition of radian. It's good to know. Basically, there's 2 pi radians is 360 degrees. So every single circle has 360 degrees, but it also has 2 pi radians. So if you want to convert between radians and degrees, you can multiply by pi over 180 or 180 over pi. So if you start from degrees, you'll multiply by pi over 180. If you start from radians, you multiply by 180 over pi. Alright, so sine is the ratio for, okay. If you have this point, you know it's vertical and horizontal displacements. You know its distance from the origin, and you know the angle. The sine of that angle is the ratio. It's the y, which is the vertical displacement, over the radius, which is the distance. Cosine is the horizontal displacement over the distance. And tangent is the vertical over the horizontal. So it's the slope of the terminal ray. And it's also sine theta over cosine theta. Alright, so if you have radius r, angle theta, the intersection occurs at r cosine theta, r sine theta. And unit circles have radius 1. And in a unit circle, it's just me cosine theta, sine theta, because that r is just 1. Alright, make sure you know your unit circle. Hopefully this is not your first time learning it. It's most important that you pay attention to things in the first quadrant. The sine and cosine of those angles. This is what the graphs look like. Sinusoidal function is any additive or multiplicative transformation of f theta equals sine theta. Sinusoidal functions can also have cosine in them. So sinusoidal function just means any sine or cosine function. So period of sine cosine is 2 pi, and the frequency is 1 over the period. So 1 over 2 pi is the period, the frequency of sine cosine. The midline is the horizontal line that kind of cuts the minimum maximum values in half. So for sine cosine, it's just y equals 0. And the amplitude, you do max minus min over 2. Oh yeah, midline is the average of the max and min. So it's the distance from the midline to max or min value. For sine cosine, it's just 1. Flexion points at their x-intercepts. Cosine is even, sine is odd. This is a good diagram. I would just soak that in for a minute. The amplitude gets changed by the a value. The period gets changed by the b value. The phase shift gets changed by the c value. And the midline gets changed by this d value, which is the thing you're adding. So on the inside, it's phase shift. On the outside, the thing you're adding is change the midline. Okay, so note, if you have it of this form and you're doing the transformations, what you would want is you're like trying to graph it. the C value is going to be your horizontal shift. The K value is going to be your horizontal, it's going to be changing your period, but it's going to be your horizontal dilation. So notice I'm working from inside to outside. You start by shifting it, then horizontally dilating it. And then your A value is going to be vertically dilating it. Your D value is going to be vertically shifting. So sinusoidal function models are good for modeling periodic scenarios. When you're doing it, if you're not using your calculator, you can't use your calculator. You can use either sine or cosine. It's important to know the midline, period, amplitude, and phase shift. And you'll want to see the if you have it's good to sketch a graph first off of your data versus the parent periodic function and see how much you need to translate it to make the midline points line up. I'm not sure if that makes sense. If it doesn't make sense, this is one of the hard parts. I would recommend going back and reading this. Another important thing, the midline, the amplitude, and the midline, the amplitude, and back to the midline. The midline to the max, to the midline, to the min, to the midline. Those are all 1/4 of the period. You can see better in the diagram. Right. It's all good to know. Just want to save time. So tangent, it gets similarly affected by transformations to pretty much any other function. But instead of the period going from 2 pi over b, or absolute value b, it goes to pi over absolute value b because the period of tangent is not 2 pi, it's just pi. And yeah, here are a couple different ways to think about tangent. Pause the video if you need. Alright, so inverse trig functions, sine inverse, cosine inverse, tangent inverse. So sine's domain gets restricted to this, sine's domain gets restricted to negative pi over 2 pi over 2, cosine to 0 pi, and tangent to negative pi over 2 pi over 2. Sine inverse, the domain is negative 1 to 1. Same for cosine, but for tangent inverse, the domain is all real numbers. So that's just the restriction just happens so that the graphs can be invertible. So they can have inverses. Alright, this is good to know. I'm not going to go over everything. Often you'll have to solve for the solutions. Or it's good to solve for the solutions from 0 to 2 pi. And then use those to find the other solutions by using the period of trigonometric functions. Graphing calculator you should always use if you can, but if you don't have it, then you'd use algebraic manipulation trig identities often. Alright, this is good to review, but I don't have a lot of time. Alright, so secant, cosecant, and cotangent. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So this is all set here. It's undefined, like where the thing that they're reciprocal of is equal to 0. So, for example, secant is equal to 0 where secant is undefined where cosine is equal to 0. Cosecant is undefined where sine is equal to 0, and cotangent is undefined where tangent is equal to 0. Okay, you should really know these. Sine squared plus cosine squared equals 1. That's the most important one to know. And the other two can be derived from that. So just make sure you know that. These are the 3 Pythagorean identities. Make sure you know these two. The most important is sine and cosine sum identities. So, the minus is important, but as long as you know, like for example, you could replace b with negative b, and this would still hold true, but that would be the same thing as sine of a minus b, so you can kind of derive. So this would be sine a cosine of negative b, but cosine is even, so this should be cosine b. Over here, this would be sine of negative b, which is just minus sine b. So that's where this comes from, these sign changes. Anyways, you can also use that if you let a equal b, you get sine of 2a, but that'd be sine a cosine a plus cosine a sine a. So that'd be 2 sine a cosine a. A similar thing can be done for cosine. I just like to note the most important one to know here for cosine is the top one. I wouldn't memorize anything else. And really, you just need to memorize the sum, and you just need to memorize the sum ones. Alright, trig identities. These ones, I would just focus on the top two if you're going to memorize them at all. So cosine of sine inverse is equal to sine of cosine inverse, which is the square root of 1 minus x squared. Don't spend too much time on that, though. Rectangular coordinate system, it's about displacements from the origin. Polar, it's r theta, where r is the distance from the origin, and theta is the angle that it's getting rotated by. So this picture is kind of helpful, I think. So if you're going from polar or rectangular coordinates, you just do r cosine theta comma r sine theta. If you're going from rectangular polar, first you have to get the r by taking the square root of x squared plus y squared. And there's two different formulas. It would be theta's tangent inverse of y over x if x is positive, but theta is pi plus tangent inverse of y over x if x is negative. Complex numbers can be applied on the complex plane. So this thing. So they can be represented in rectangular form or rectangular coordinates. So this x plus yi. Or in polar form. So r cosine theta plus I sine theta. Or you could have it expanded out. Like r cosine theta plus r sine theta, or you factor out the r. Anyways, the techniques before, you can just convert the different coordinate forms, and then you can use that to convert from a plus bi to r cosine theta, r sine theta form. Anyways, alright. Regular functions take coordinates as x coordinates as inputs and output y coordinates. So y equals f of x, but polar functions take an angle measures and output displacements from the origin. So r equals f theta. Positive theta counterclockwise, negative clockwise. Negative r means it's being reflected from where it normally would be. So, oops. Yeah, this is what polar functions look like. The average rate of change, it's r2 minus r1 over theta 2 minus theta 1. So the y's and x's become r's and thetas. Or f of theta 2 minus f of theta 1 over theta 2 minus theta 1. So yeah, if it's increasing or positive, think about what that means. So the distance from the origin is increasing. The r value is increasing, but it's positive, which means it must be getting farther away. So, but if it's negative and it's decreasing, so it's already, imagine, it's already over here. Like, this is the angle, but then it's already over here. The r value is negative. It's decreasing even more, so it's getting farther away. Both those cases would be farther away. And the opposite is true if it's decreasing positive, increasing negative. Distant origin is decreasing. You really don't memorize that. You can probably won't get a question like that, and you can kind of reason your way through that either way by just thinking about it. Yeah, so increasing, decreasing on an interval, or vice versa, means a relative minimum or maximum, so which is a point relatively closest to or furthest from the origin. So relative min, closest to, relative max, furthest from, relatively. And then function values, yeah, you can estimate using the rate of change, create a linear approximation. Anyways, I wish you luck on your AP exam. I know there's a lot. I'm posting the slides in the description of this video. But yeah, I wish you luck on your exam, and I hope that you have a good rest of your day.